So last time we talked about the Viterbi algorithm, which finds the most probable Markov chain in the hidden Markov model that generates the sequence in hand. Then we talked about the forward algorithm, which is really what is the probability that that Markov model would produce that sequence at all, and therefore you're summing over all of the chains that could produce that sequence. And the interesting thing is that both of those tasks can be computed relatively efficiently, and that's what makes hidden Markov models so effective. Otherwise, it would just be a formalism that had no real application or real utility. There's a third classic algorithm that's associated with hidden Markov models and that people oftentimes want to use when they're studying a particular sequence or studying how the Markov model classifies portions of that sequence. And so I won't have time to give you the algorithm, but I do want to tell you what it does, what its end result is, and then you can look in the notes that I've passed out about the backward algorithm. So backward algorithm computes the probability that pi I equals k given x. That's it. Okay, now next thing I'll talk about, now that needs a little explanation. This is the sequence. Last time I was talking about S, but it was always x1 through x something, so we might as well just call it x. So this is the sequence at hand, or in hand. This is the sequence you're looking at. You're trying to analyze with respect to the hidden Markov model. This is the this is saying that the ith step of a Markov chain is in state K. Okay, so this is really just saying that when the hidden Markov model generates x1 through xi, it is in state K. Okay, so this is the probability that you're in state K at the moment that you're producing the ith symbol of x, given that what the Markov chain actually produces, or that the Markov model actually produces, is this full sequence x. So if you really want to think about it, what it's trying to get at, we were talking last time about the fact that there are many, many different Markov chains in a hidden Markov model that could produce a particular sequence, x. And we talked about finding the Markov chain that was the most probable out of those. And we also talked about how to compute their sum. Now we want to know, really, what is the relative frequency, if you will, that those various chains that produce x go through state K at the ith step. Okay? So it really has to do with what's the centrality of this state K in the ith position in the Markov chain. Suppose, so the question comes up is, why do you want this? There's always the how to compute it, but that's the backward algorithm, and I'll let you read about it in the book or in the notes. But a more fundamental question is, why would you want to learn this about your sequence and about your hidden Markov model? What information does this really give you about, ultimately, about your biological sequence? Anybody suggest anything? Well, you know, these different states in the hidden Markov model have different significances. We've just been looking at the particular case of CPG islands, but in general, different states in different hidden Markov models are saying different things biologically about what's in the sequence. So, you know, let's just imagine this is the state that is associated with some active site in a protein or something that's highly significant, or a cleavage site in acceptor-donor exon-intron boundaries. You can make up all kinds of things where this is the critical state that identifies what's going on there. Okay? And when we focus on a particular character I in the sequence and on a particular state K that it may have some significant, some biological significance, then you're really saying over all the different ways that the hidden Markov model could generate X, what's the probability that they overall will be declaring this character I to be in the biologically significant region of that sequence. So that's very useful information, which is separate information from what's the most probable full chain, or what's the total probability that the Markov model would produce a particular sequence. It's really homing in on a particular aspect of the Markov model that may be significant and a position in the chain, a position in the sequence that's of interest, and asking if the Markov, given that the Markov model is going to produce this sequence, what's the probability that it will be declaring position I in the sequence to be of whatever biological meaning state K has. Okay. So anyway, try to absorb and understand why you compute this, why you want this, and read in the notes how it's efficiently, and again, it's something that can be efficiently computed by dynamic programming, only they give it a different name. They call it the backward algorithm. It's got nothing to do with backtraces, by the way. Okay, but I don't have, given 3 more lectures for all the things we have to talk about, I didn't want to spend any more time on that. What I do want to say a little bit about are profile hidden Markov models. This is the last part of the notes, and I won't be able to do this in full generality. I also have some new notes on hidden Markov models that I'm going to pass around. These new notes also talk about basically profile hidden Markov models. I'm not sure they call them by that name, but they probably do. They're somewhere. And I wanted them to pass out these in particular because this talks about PFAM, which is a database that you've used, but it really connects what the content of PFAM is to the methodology of hidden Markov models. And it also talks about GenScan, which is a program that takes an anonymous DNA and tries to identify the genes, particularly in eukaryotic DNA. That's a complex thing. And that is a gigantic hidden Markov model that models gene structure. And this handout says a little bit about that as well. So that's why I wanted to pass out these different notes. So let me start those around. Make sure I've kept one for myself. Okay, so in profile hidden Markov models, these are really probably the most common hidden Markov models that are used. If you look in PFAM, that's many of them there are of this type. So this is modeling protein families. Well, it doesn't have to be proteins, but protein families where one has a pretty good multiple alignment of them. Of many members. Of the family. So when you have a multiple alignment, you have that where you have a lot of representatives in that family, and you're able to get a multiple alignment that you trust has some ability to capture the general structure of the members in that family, then from that multiple alignment you can construct a hidden Markov model which really expresses what's going on in that multiple alignment and allows you to compute how well other sequences fit that hidden Markov model. So let me take one from the second notes that I'm just passing out here. The profile hidden Markov models all have a very similar structure. Basically, I'll use their notation. You have a backbone here which gives particular characters or gives a distribution of characters. So this really, these are characters along these are the columns of the hidden Markov model. Okay, so columns of the multiple alignment. Sorry. Let's just say we have three M0 through M3, and in each one of these, what you would generate. Here you generate a character, a specific character with some probability. Generate character, it's just bad grammar. There's a probability distribution what character is emanated here? Emanated or emitted? So in this position, there's a probability distribution for what's emitted, and similarly, probably a different distribution in the second position, and so on. So each one of these has some probability distribution for what's being emitted. What does this look like so far if this was my hidden Markov model? Can anybody see that this is, we've already talked about this in some length, but some different way. They're just a different language. A what? Yeah, this looks like our standard old position-specific scoring matrix. You know, if these probability distributions, if this is, let's say, the frequency of the different characters you see in the leftmost column, and this is the distribution of what you see in the next column, and so on, then this would just be a position-specific scoring matrix or a profile. And then if we asked for, if we had a particular sequence in hand, and we were asking for what's the probability, what's the most probable path through here that generates that sequence, it would just be the product of the various probabilities of generating the appropriate character or emitting the appropriate character at each position. Okay. But a hidden Markov model is going to have more power than that. It's going to allow insertions and deletions, okay, so that relative to the multiple alignment or relative to the profile that was based on the multiple alignment, a new sequence might have some insertions or deletions so that you don't have to just line up the first character in the new sequence with the first character in the multiple alignment and the second character in the new sequence with the second character in the multiple alignment. That seems very rigid and doesn't allow the flexibility of insertions and deletions that we're used to when we were talking about alignment. So we want a hidden Markov model that allows insertions and deletions, but still basically is talking about using the idea that if this hidden Markov model is the generator of sequences, each Markov chain through it has a certain probability, and therefore for any particular sequence, there's a probability distribution on the particular Markov chains in here that would generate it. And then you want to ask all the standard questions. If you have a particular sequence, what's the most probable path through the hidden Markov model that would generate it? And therefore, there may be some insertions and deletions relative to the multiple alignment. and so on. So what does this thing look like structurally? You have insertion state here. Should I draw with a diamond? I don't know. We don't have to keep those conventions. Okay. You could have things that go around here, and this is another insertion. Okay. Goes around there. Down there. And so on. I'm not going to draw in each one, although I'm only saving myself one step. Okay. Here's an I3. Okay, and then this goes on to the next one, etc. So we have these insertion states. Well, I don't know. There's only one missing here. I2. And these also have some probability distribution associated with it. What is being inserted? Okay? So we have a probability that we go to insertion state after these are called match states, by the way. The M's are for matches. So you're given a sequence, a new sequence, and we want to understand what's the probability it would have been it is generated by this hidden Markov model. And whenever you have a character in the sequence that actually, is going to be generated in one of these states, it's sort of considered to match the hidden Markov model, although it's not literally a match because this has a probability distribution. But anyway, it's an emit state. You're emitting a character there from the multiple alignment, whereas this is an actual insertion of something that's you didn't want to spend your capital. You didn't want to go on to the next state here, even if that permitted the next character to be generated or emitted, because the probability might look too low. So rather you go up here and you insert. You're considering that you're inserting into the new sequence something that wasn't there from the multiple alignment. All right, so all of these edges will have certain probabilities. This has probability distribution on which particular character is inserted. And then we also want the ability to delete from a character, the new sequence as well. And you could insert and then delete, or you could match and then delete. And the interesting thing about the deletes, and from a delete you could go on to an insert, or you could go on to your next match. Or you could go on to delete again. Okay. Now, what are you deleting from? You're deleting essentially from from these guys. You're deleting a position from the multiple alignment. And so we don't want to let a delete state loop through itself because you don't know how many times it's done so. You don't know what would then be the next match state to go to. So instead, we're going to have these delete states explicitly laid out there, and which match state they go to. I'm actually off by one. D1 is actually supposed to go to. Yeah, so this is delete what was going on in here. Just essentially ignore that portion of the multiple alignment, and therefore the next thing you would do is either move on to the next part of the multiple alignment or delete again. If you delete the second one, then you're going to go on to M3. And if you delete the third column of the multiple alignment, you're going to be moving on to the next one that's over here. And finally, there's an end state. Okay? So this is what is the general structure of probably the most common hidden Markov model that people talk about and use. And so these are called profile hidden Markov models or protein hidden Markov models. And the CPG islands are a nice way of introducing the idea of hidden Markov models. But these are typically, if you talk to somebody who hasn't studied a lot about hidden Markov models, they might think that this is what your classic hidden Markov model in bioinformatics looks like. Okay, match states which come from a multiple alignment, probability distributions which have to usually reflect what the frequencies are in that multiple alignment. These also may be log odds scores where you have some alternative, usually the totally random model. So these are either derived directly from the frequencies you see in the multiple alignment, or it's the frequencies divided by what you would see if what was there was just purely random. And so these are the match states along the backbone here, insertion states, and deletion states that have that kind of a structure. And again, the hard work in getting a hidden Markov model is knowing what the right probabilities should be on all of these edges. And that comes from training data where you look at actual multiple alignments and see what the best parameters are here that fit the data that you have in hand. Okay, we haven't really talked about that aspect at all except for these probabilities here. There actually is a program that people may want to use. I think it's called Hummer, or HMMER, that would take in multiple alignments and actually produce the hidden Markov model for you. And it's available on the web if you look for it. Okay, so that's really about it. The notes, the second set of notes, talk about how to do multiple alignment if you have a hidden Markov model for a family and you have new sequences. How do you multiply align those new sequences and so on? But we're really running out of time, so I think this is a pretty reasonable introduction to hidden Markov models. I think about all the things we haven't talked about. One is PSI-BLAST. So before if I don't get to PSI-BLAST in the next couple of days, somebody stop me and remind me, because it's an alternative to this kind of very structured approach to sequence families. PSI-BLAST kind of builds these models on the fly, and you've had a lab using PSI-BLAST, but we hadn't really talked. And if you read the tutorial on PSI-BLAST, you should be able to see the commonalities here. But PSI-BLAST, in a sense, you start with a BLAST query. You find multiple hits. So these are things that are related to your query, and you build a model of those. It's a very simple model, but then you use that model to try to find additional sequences that fit that model, and you build out in that way. Maybe this is all, people already understand that, and maybe this is all I really need to say, or given our time, will say about PSI-BLAST. So it's not like you already have a family that you really know are related by some function, and you're going to build a hidden Markov model or even just a position-specific scoring matrix that tries to represent it, or a prosite regular expression. That's an approach where you really believe in your family already, and you're just trying to get some kind of characterization of it that would be very useful. PSI-BLAST is sort of, it's sort of the, I shouldn't use that. Anyway, it's a very much more naive kind of approach, because you do a BLAST search and you get all these sequences. You don't really know that they're related to your query. It's just the first guess of BLAST in the first case. But then it builds a model of those as an ungapped position-specific scoring matrix, uses that model then to find additional sequences that didn't come up on your first iteration of BLAST, but are now picked up because the general philosophy is that you can find additional sequences more sensitively when you're querying with, or you're comparing your new sequence to a representative of a set of sequences, such as a position-specific scoring matrix, rather than just a single sequence. So then the new sequences that are found, they're included in the model. So you see from your seed, from your first query, you go out a little ways to all the sequences you can find, make a model of those, go back in the database, find some more sequences, make a model of those, go back in the database, get some more sequences, make a model of those, and then you can go from A, to Z through a few steps. And this is PSI-BLAST is, I think, what most people use today to find distant connections, distant relatives. Okay, but if you, I think I have this on the either on the previous midterm or on the previous final. By the way, I posted the two old finals, the final exams, on the web now, from 2000 and 2001. PSI-BLAST is a little bit dangerous because you can pretty much get from anywhere to anywhere if you just iterate long enough. I mean, it does stop once if it doesn't find anything new in some iteration, it stops, or you can cut it off, or you can use some e-value to cut things off. 3 or 4 iterations is about all that people normally do, but you really can get from anywhere to anywhere. It's like the 6 degrees of separation, or the handshake business. How many handshakes are you away from some random person you name somewhere on Earth? And it's not supposed to be that many. It may be difficult to find them, but if you were able to list all the people you shook hands with and all the people they've shook hands with, and so on, it's supposed to be only a few hops, 6 or 7 on average, between any two people. So that makes PSI-BLAST dangerous, and that's a question that I asked either in one midterm or one final. What are the advantages of PSI-BLAST, and then what are the dangers of PSI-BLAST? And in the PSI-BLAST lab that you did, hopefully we had one example where PSI-BLAST was useful in finding a relationship that wasn't immediately obvious, and then one where it was finding some nonsense. The nonsense is frequent, and you have to evaluate. Once you find a PSI-BLAST connection, you have to use whatever else you have at your disposal to figure out if that was a meaningful one. Okay. That goes back to your tolerance for false positives and false negatives. And that's something, again, you really, I want you to understand from this class. So that's really it on PSI-BLAST. Okay, don't remind me to talk more about PSI-BLAST, because that's it. Scratch that one off. Next thing I need to talk about for sure is where the substitution matrices come from. Okay, we've used PAM matrices, I know in the XParal. We've used Blossom matrices, I think, at some point, or talked about them. And they really follow, in many ways, some of the same ideas that we've talked about in the last couple of weeks, particularly log odds ratios. Okay, so if I don't get back to substitution matrices, please do remind me.